All right, we're at the second to last lesson. So we'll have one more on Monday, and then that'll be all the new material. A week from today, Wednesday, will be final exam review. We're actually only going to be two problems on the final, which I'll be composing this weekend. That'll have brand new material that hasn't been tested before. It's on Laplace's equation. So I'm going to cover one of those cases today and the other on Monday. Okay. So a problem we're going to be looking at today a boundary value problem, and on a circle, or you can think of it as a disk, really, and the radius to be r tilde. I have r tilde because I need capital R for something else a little later on. So Laplacian view is 0 on the interior of the disk. And then we have a boundary condition, u is equal to some given function g on the circle. So this is called the because the Dirichlet boundary condition. And we're solving the PDE on the interior. That's why it's called the interior Dirichlet problem. Now, because we're working with a circle, it makes sense to use polar coordinates. That's why I went to the trouble last time of rewriting a Laplacian in polar coordinates. So this is the PDE that we'll be solving expressed in those coordinates. So our polar coordinate variables are and theta, working on this domain. So with regard to the polar variables, what we have is it's a rectangular problem in that coordinate system. And then our boundary condition is that when little r is equal to capital R tilde, then it's equal to g. And g has been expressed as a function of theta since it's defined on the circle. So what we can do to solve this problem, we can use separation of variables like we have elsewhere. All right, so how we proceed is, and this is why I needed, I have r tilde, I have capital R down here. U is assumed to be a function of little r times a function of theta. So these functions are called capital R and capital theta. So we substitute this into the PDE. And get this. And so going through the usual separation of variables manipulations, we obtain this. And this expression depends only on little r. This is a function only of theta, so they must be constant. And k is that separation constant. So then these are the ODEs that we get by taking these two expressions and rearranging, and then rearranging this equation here. So now, like before, with separation of variables, we have to consider cases of k being positive, negative, or 0. Okay. K equals 0, then theta is a linear function. Like a capital theta is a linear function of little theta, but it has to be 2 pi periodic. The only way that can happen is if b is 0, so then theta has to be a constant. If k is positive, then capital theta has this form. So it's linear combination of exponentials. The only way that can be 2 pi periodic is if a and b are both 0. We only need can only consider non-trivial solutions, so we forget about that case. And then when k is negative, theta is equal to this combination of sine and cosine. So for this to be 2 pi periodic, we need lambda to be a positive integer. So when we put all of that together, our ODE for capital theta, we have a family of solutions, all of this form. And here we have n equals 0, 1, 2. So 0 is a possibility, in which case this would be 1 and this would be 0. So we would just have a constant. So that is allowed. Okay, so now we have our form for capital theta at least. And now we can turn our attention to the other ODE for capital R. That has this form now. And because so what we had before was some separation constant K, which we now know has to be non-negative. Or sorry, it should be non-positive. Positive is ruled out, but it can be 0 or it can be negative. K being equal to minus lambda squared, lambda has to be an integer. So that's how we get this. That's how we get that n squared in here. And that's called an Euler equation, something that may or may not be covered in a first course on ODEs. And okay. But we could just go ahead and jump to the solution of that. Or it can be solved in this approach. Make a substitution, z is equal to, well, actually, it would be not x, natural log of r. But once you go through that whole process, and I won't go through the details of solving it, but the bottom line is your general solution has this form. So it's a linear combination of r to the n for whatever n this is, and then r to the minus n. And for constants a and b, that would relate to the initial conditions. But the thing is, we need the solution to be well defined at the center of a circle. R equals 0. That's the center of a circle. We can't be taking a negative power of that. So we drop this term. We require that capital B is 0. So now our a solution would have this form. We have our capital theta solution here, and then we have r to the n. And for convenience, I've included this constant factor of 1 over r tilde to the n, because that way, when we consider the boundary, we set little r equal to capital R tilde, and it cancels out. So then we only have this part. So it makes it easier to find these coefficients. So now we can describe our overall solution to our boundary value problem as this linear combination. So it's reminiscent of some of the series we see before, like a Fourier series. So we just have to make sure that this satisfies the boundary conditions. So how do we do that? The boundary condition is applied when little r is equal to capital R tilde. So we go ahead and make that substitution. And what we end up getting when we do that is these are the formulas for AN and BN. And the reason why we have this factor of 1/2 is so that we can use the same formula for all the A's, including A0. So when you have an interior Dirichlet problem for a circle, you can jump directly to this being the form of your solution and use your boundary condition, u is equal to g on the boundary, and use v's for your coefficients. So these are key equations to take into account when you're solving a problem of this kind. So any questions at this point? Now we have another way to express the solution. And that's called the Poisson integral formula. That comes from a solution formula that I've shown you. Now for this, I'm instead of using R tilde, I'm just going to use capital R because I no longer need capital R function that I had before. So this is what we get. So what I've done here, here's my so what I've done to get this is if I take these formulas for AN and BN and substitute them in here, then here we have an integral, here we have an integral, here we have an integral, all from 0 to 2 pi. So so what I can do is I can move everything, all of this, inside the integral from 0 to 2 pi. And once I do that, and I still have 1 over pi on the outside, then I have this. And g of alpha is involved in every single integral of these a's and b's. So that can be factored out, but still kept inside the integral. So that's why it's sitting out here. So what I could do now is focus on this expression that in the square brackets that is independent of the boundary data, and see what I can get. Okay. Now here I use a trig identity. This is a cosine of a difference, cosine of n theta minus n alpha. So that allows me to condense this to this. And then I can express cosine of anything as e to the I times that angle plus e to the minus I times that angle all over 2. So we have a factor of 2 pulled out here. And all I've done here is just break a summation into 2. Now, in both cases, these sums, these are geometric series. Now, the sum of a geometric series, when you have some number that's less than 1 in absolute value raised to the nth power, it's equal to the first term divided by 1 minus what's being raised to that power. So the general formula for the sum of a geometric series is what I've applied here and here. Okay. Here I've just multiplied top and bottom by capital R, just to reduce some of the clutter. And then, I put everything over a common denominator. And just as I broke this down into a sum of exponentials, I've used this relationship again in reverse, and that's what leads to this cosine right here. Okay. And then I've also used that relationship to simplify what I have up here, and that's what gives me this. And also from like foiling all this out. And then incorporating this plus 1 with the same common denominator leads to further simplification. And this is what I'm left with. So this is my final result, and that is called the Poisson integral formula for the interior Dirichlet problem on a circle. So what you can do is you can take your boundary data expressed as a function of theta from or alpha going from 0 to 2 pi, so a function defined on a circle of radius capital R, and then evaluate this integral, which, given the expressions here, could be extremely difficult to evaluate, or more than likely what you would do is evaluate it numerically. Now, so what's interesting is if I take this integral formula, now I'm evaluating this at r theta in polar coordinates. So if I plug in 0 for both r and theta, little r and theta, so that goes away. All these terms will go away, and I have r squared over r squared, so that cancels, and I have 1. So all that's left is this. But this is equal to the average value of a function g on the interval 0 to 2 pi. So the value of a solution at the center of a circle is equal to the average value of g on the boundary. Actually, all I have to do is plug in r equals 0. It doesn't even matter what theta is, because r equals 0, that's the origin. That's the center, regardless of the value of theta. And we still get this. So this is something that Poisson's integral formula makes it easy to see. Also, this expression comes from the law of cosines. So the denominator here, okay, I should say this is the square of, if we take a triangle that has vertices 0, 0, r theta, and capital R alpha, and then one of the legs of a triangle is opposite this angle of theta minus alpha, then this is the length squared of the opposite side by the law of cosines. Now, here we're solving this PDE only on a circle. What if you have a domain that's not a circle? What you might be able to do is, if you're able to define what's called a conformal map of whatever domain you have to a circle, then you can use Poisson's integral formula on that circle that results from a transformation, and then apply the inverse of that conformal mapping to go back to your original domain. So what we've seen here can be useful for solving this kind of boundary value problem on domains other than a circle. Okay. Do we have any questions about this? or about any ongoing homework problems? Or anything else for that matter?
Are we going through an example for this sort of problem?
Okay. I do not have one in these notes. I can attempt to make one up. With disclaimer that it's not easy to do on the fly. So I apologize in advance for any mistakes. Okay, so we have Laplace equals 0 on the say the unit disk, and we'll assume that and this corresponds polar coordinates, u of r theta is equal, or u of 1 theta is equal to, let's say, sin theta minus sine 2 theta. Okay. All right. So if I take my, so I'm not going to use a Poisson integral formula for this. It'll be easier in this case to use the other solution formula, which I'll grab real quick. Okay. Whoops, something went very wrong here. Okay, let me try it again. Oh. It's not what I wanted. Hold on. Okay. All right, so here we have our, so g of theta in this case is our initial data. Or not boundary data, boundary data. In this case, because we're working on a unit circle, radius 1, our radius r tilde will be 1 in that case. Okay, now by orthogonality, what we end up with is here we'd be filling in our data sine theta minus sine 2 theta in for g. Well, sines are orthogonal, all sines are orthogonal to all cosines, so these integrals would turn out to be 0. Here, if I have sine theta, so which matches this with n equal 1, so I'd have b1 is equal to the coefficient of sine theta, which is 1. And then I'd have b2 is equal to the coefficient of sine 2 theta, which is minus 1. All other b's are 0. So if I take into account all of this up here, our solution expressed as a function, as in polar coordinates, will be equal to, so we'd have r to the first power times a1, well, that part's 0, b1 times sine theta. Okay. And then I move to n equal 2, and that's going to give me r squared. I have a minus because b2 is equal to minus 1. And that is my solution. So what happens is when your initial data is a linear combination of 2 pi periodic functions, such as this, then the coefficients, your a's or b's, depending on whether these are sines or cosines, you can read off a coefficient of linear combination, as we've seen in some other problems. And what's going to be multiplying each of these in your solution are the appropriate powers of r, corresponding to whatever value of n you have here, like sine or cosine n theta. Now, in this problem, I had the unit circle. If I had a circle of a different radius, then that would have to be taken into account down here. Questions about this?
Can we also go over an example for non-circular domain?
That would not be practical to do on the spot. Okay, no, I mean, you're not going to have a test problem like that anyway. That was just me talking about here's the number of situation where this can be used. Because conformal mapping is something you learn about in a complex analysis course, which I haven't taken since 1989. So I appreciate you being understanding on that. Now, the next lesson will be on a somewhat different domain. It's going to be an annulus, so the area between two circles. So I will cover in detail how to handle that situation. Actually, if I take a look at the homework problems for this lesson. 33. Okay. Okay, yeah, all of those homework problems deal with a circle of some radius. Other questions? Okay. All right, so I will stop recording at this point. I will have the any practice information and the test composed in time for Monday's class. Okay, and I'll